This is part 2 of the Medjil guide, focusing on analyzing the EDMI calibration results. Let's just jump over and have a look. Click EDM calibration, EDMI calibration. And in here we have a calibration report, which is this one here, and a calibration certificate, which is this one here. So you can think of the calibration certificate as a simplified version of the calibration report. The certificate does not contain any information that is not in the report, and the report has greater detail about the EDM instrument calibration results. So let's do a quick comparison between them. For this comparison, I'm just going to focus on showing where the report matches the certificate. We'll go through a report example in real time a little later on in this video. So on the left here, we have the calibration report, and on the right, we have the calibration certificate. I've highlighted in green the sections that are present in both. Once again, the entirety of the calibration certificate is actually present within the report, so it will be completely green. So first up, we have some introductory information about the calibration site and some of the parameters that we entered when we set up our EDM instrument calibration. We've got our instrument details here. Then we have some specific baseline details. So in this case, this is the Gold Coast baseline. Next. So here is a first example of a difference. In the report, it shows the certified baseline distances from the Gold Coast baseline that have been used in the EDM instrument calibration, whereas the certificate skips this. Next, we have the instrument correction values, which are present in both. Then we have the least squares adjustment summary, which is present in both. And from here on out, the report has a pretty significant amount of information, which is not present in the certificate, which we'll look at a little bit later, but we'll just skip forward now. Towards the bottom of the report, we see this comparison of raw observations to certified slope distances in the report, which is also in the certificate. And then right down to the bottom, we have the report notes and data warnings. So that's the difference between the report and the certificate. I believe the intention is that depending on the level of detail that the user is interested in, they could look at either the report or the certificate to verify their EDM instrument calibration. Currently, there's a couple little statistical tests in the report that are really quite important that haven't made their way to the certificate just yet, particularly the statistical test A. So as it currently stands, I do recommend that you take a look at the calibration report over the calibration certificate. However, I've had a bit of a chat to Landgate, and in future updates, they might be adding some of these things to the certificate. So let's take a look at the calibration report and explain some of the different elements within it. This will, by extension, be applicable to the calibration certificate, as we've just mentioned. Here you've got two little icons. The one on the left is the certificate. The one on the right is the report. So let's open this report and take a look. First up again is some of the introductory information. It talks about the site and various other things, instrument operator, operation date, etc. Then we have our instrument details, which we set up earlier in the instrument register. So the total station or EDMI, prism, thermometer, barometer, and hygrometer. Some information about the baseline itself. So in my case, it's the Gold Coast baseline. Certified baseline distances used. And the first part that's going to be relevant to us is going to be estimated instrument corrections. Instrument corrections are displayed in a number of formats, which can get a bit confusing. However, these are actually all mathematically equivalent. For more information, I would recommend you open up the Medjil technical manual, take a look. So I'll show you that relevant section now. Click on resources, click on technical manuals. I'm just going to open it in a new tab. So you can click on 3 EDM instrument calibrations. So section 3.1 gives an explanation about the different systematic errors in EDM instruments that we are trying to solve for and correct for. Section 3.2 shows a full mathematical model of the instrument correction. So in this model, you'll see 6 unknowns. ZPC, 0-point correction, SCF, scale correction factor, and you've got this 1C, 2C, 3C, 4C, which is the 4 cyclic parameters. So typically the 4 cyclic parameters have a minimal effect on the instrument and don't need to be corrected for. As such, it is standard practice to not test for cyclic errors, unless you have a particular reason to do so. So if you don't test for them, this equation can actually be simplified by removing all of this, which is where we get the version that we see in here, 0-point correction, scale correction factor, times distance. So let's ignore this first equation here for now. I'll come back to that. Let's have a look at this equation here. Might even scroll in a little bit, make it a little bigger. So this states d dash, where d dash is the corrected distance in meters, is equal to ZPC, which is the 0-point correction in meters, plus CF, the scale correction factor, multiplied by D, which is distance in meters. So in this form, the scale correction factor is going to be a number somewhere either side of 1. So in my example, it is 0.999999911, so slightly smaller than 1. So it's going to slightly reduce my distances. Let's have a little bit of a look at the next form. The next form, we have the instrument correction, which is slightly different to the D dash, in millimeters is equal to index in millimeters, which is actually the same as 0-point correction, but in different units, plus scale in parts per million, which is equal to the scale correction factor we saw previously, minus 1, then converted to parts per million, multiplied by distance, now in kilometers. So just take note, we've got a lot of different units that are jumping around here. So in this form, scale is going to be a number that is hopefully very close to 0 either side. So it should be something like what I have here. So I've got negative 0.989 parts per million, which makes sense because my value up here is less than 1. So if you take this number here, the scale correction factor, minus 1, multiplied by a million, we get this value here. So we scroll back up and have a look at the first one now. You can see the first equation is quite similar in form to this third one, mainly just with the exception of the units. So ZPC is the same as index, different units. Scale correction factor minus 1 is the same as scale. You just got to take care of the units. So hopefully that's enough to sort of briefly show the mathematical equivalence of these 3 equations. Probably could go further with it, but hopefully that's enough for now. All that being said, these first 2 equations are provided as this is sort of the way that Medjil itself is really thinking about these values, and is the form that is used when completing the least squares adjustment. So you could say this is how Medjil thinks about it. This is how Medjil wants to think about the instrument corrections for the purpose of all of its underlying mathematics and statistics. But then once all the calculations are complete, it gets converted into this form. That is probably a bit more familiar to you as the surveyor. So index in millimeters, scale in part per million. So if all that's confusing, don't worry. Just come and find this equation with the index and scale, and we'll use it when assessing and or applying your instrument corrections. A quick note on entering these values into your total station. With most modern Leica and Trimble and possibly other total stations, there is no dedicated way for you to enter these instrument correction values. I know some surveyors apply these corrections by entering the scale correction as a job scale factor and the index correction by editing the prism constants as a workaround. I'm not making any recommendations either way as to if you should do this or not, but just be careful as this is not really what the manufacturer is intended for you to do. So if your total station has a functionality to add in instrument corrections, or you choose to apply the corrections some other way, these would be the values you would use, just taking care to get the units correct. If a total station does not natively have the ability to enter in instrument corrections, then you just need to ensure you're comfortable with these values being small enough as to not introduce an excessive amount of error into your work. Just remember, with the instrument corrections, you need to consider the values as well as the uncertainties when considering if your instrument is performing as expected. If you had instrument correction values close to 0, but the uncertainties were, say, 2 millimeters and 5 parts per million, well, you need to take a look at your report to see what's going on. You really want to confirm that the index and scale are reasonable and are relatively reflective of what you would expect from your instrument. So how would you do this? Well, if these values are larger than what the manufacturer specification states for their uncertainty, you might have a problem. So to make it easy, I'm going to scroll down to Statistical Test A. Medjil actually already does a comparison to the manufacturer's specs, which we can look at here. Test A is comparing the instrument corrections calculated as part of the EDM Instrument Calibration. They're labeled here as test values, and is comparing them against the manufacturer's specification of the total station EDM and prism set, labeled as manufacturer's specification. If the test values are lower than the manufacturer's specified values, then this except column will say true. In other words, if you see true, your instrument is performing within the manufacturer's specifications at this given distance. And one thing I want to draw your attention to is that for the test values here, the calculation to determine them is actually using some covariance elements between the scale and the index or constant corrections component. And that's why you see a little bit of an interesting thing here where the values get smaller and then larger again. So in my case, I have 0.4 millimeters at 20 meters as well as at 50 meters. Then it drops down to 0.3 millimeters at 100 and 250 meters. And then it jumps back up to 4, 6, 7 at 500, 750, and the length of the baseline in meters, respectively. So I must admit, when I first saw this, I thought this was an error, but on doing some more digging, it is actually following an equation recommended by Ruger, which introduces the covariances between the scale and the constant correction. I just want to mention it in case you saw it and it caused concerns for you. This did for me. Also note that these values are all at 95% confidence. So if your test values passed the test at all these distances, this is a pretty good indicator that your instrument, based on the EDM instrument calibration and all the parameters you set, is performing as per the manufacturer's specifications. Okay, so let's scroll up a bit and take a look at this section that we missed, which was the least squares adjustment summary. Now this is going to help us analyze a few things about our EDM instrument calibration. The primary thing I want to look at here is the A-posteriori variance factor. I hope I said that right. And the chi-squared test of the variance factor. Okay, so what does all this mean? In order to really get the most out of this least squared adjustment summary, let's go back and try and take a look at some adjustment basics. Now, quick note, I am certainly no expert in statistics, but let's try and follow through this with some maths and see if we can get a feel for what's going on. Then hopefully when we get back and look at this least squared adjustment summary at the end, we'll be able to get a little bit more out of it. So there's three types of errors: gross errors, or blunders, systematic errors, random errors. But what do we do with these errors? How do we deal with them in terms of how they affect our measurements? So with gross errors, we don't do them. We avoid them if we can. And if we make a blunder, we find them and we fix them. The systematic errors, we often can't exactly avoid them, but due to their repeatable nature, we can correct for them. They can often be minimized or removed by applying appropriate observation techniques. An example of this is taking two-phase observations to eliminate collimation and other errors. And then we have random errors left. What do we do with them? Well, we can perform a least squares adjustment on them. to try and minimize them. So we do our absolute best to remove gross errors and systematic errors. For example, we take sufficient and accurate atmospheric readings such that we can model the temperature, pressure, and humidity to a high enough accuracy across the EDM baseline. We would use one prism, which removes the differences that might exist between two prisms. Then if there did exist some small eccentricity error in the prism, well, it would actually probably just be lost in the index correction. A side note too is that using a single prism is actually a requirement for traceability, as the calibration is of an EDM instrument plus prism set. We try to be highly precise when leveling over the pillars. So typically the tribrac bubbles can be a bit rough. So if you have a plate bubble which you can rotate around, you can then level it to a much higher accuracy. We also have a preference for pillared EDM baselines over ground mark-based baselines. In Queensland, we don't have any more ground mark-based baselines, but these had inherently significantly more error in leveling over a mark, that is. So the goal is to quote-unquote get rid of everything we can and to have just the random error left going into the least squares adjustment. So a least squared adjustment deals with only random errors. So what's the process in practical terms? We collect our EDM distance observations, taking care to avoid any blunders or gross errors as we go. Then we work through to correct for any sources of systematic error as best we can. We also work to define how accurate we think our EDM distance observations are going to be into the adjustment, and we call this the Apriori uncertainties. In Medjil, this is done with the uncertainty budget. These are used in the adjustments as weights. I'll expand more on this later. Then we perform a least squares adjustment where the unknown systematic errors of index or constant correction and scale correction are solved for. This is assuming we are not doing the 4 additional parameters, cyclic parameters. And in the process of this, and as per the inherent nature of least squares adjustment, we are minimizing the sum of the residuals squared. So here's a graph. This is actually the results of the EDM instrument calibration that I'll use as the example for the rest of this video. So you'll probably recognize it by the end. But here we have distance on the x-axis at the bottom. And here we have what we measured versus the certified distance of the baseline. So the closer we get, the zero line's actually here, the closer we get to 0 here, the more we agree with the certified distances. So what we are looking to do here is adjust these results and find a line of best fit that represents the estimated instrument corrections of index and scale. So here we go. The results of the EDM instrument calibration on this data return the following estimated instrument corrections. Index is equal to 0.65 millimeters. Scale is equal to negative 0.89 part per million. So a quick note here, as we're dealing with a least squares adjustment of one dimension, that being length or distance, what we can see here is actually called linear regression, which is the most basic form of a least squares adjustment. Okay, cool. How do we get this line? How is it determined? So this line of best fit is determined by minimizing the weighted squares of the residuals. Let's just drop the weights out for a second and just focus on the residuals at first, just for simplicity's sake. So we can think of this as the square of all these black lines that I've drawn in here. We minimize the distances between these points and the line of best fit squared. So all these black lines. Now, that's a bit confusing. Here's another way to think about it. So you can actually think of this as physical squares, where the length of the side of the squares is equal to the residual of the distance from this point to this line. So you have all of these squares for all these different points, and the goal is to minimize the area of all of these squares added together. So here we have a point, we draw a line from it to the line of best fit. That distance becomes one side of the square, we draw the square. Picture this repeated for all the points in our data. We minimize the sum of the areas of all these squares. Now I haven't drawn them all here, just to keep it a little bit clean and easier to visualize, but it would be for all of them. Now if you're still following, let's add the weights back in. So here we've added the weights back in. I've displayed it as residual multiplied by weight multiplied by residual, but you could think of this as residual squared multiplied by weight. It's mathematically the same. The reason why I've shown it in this form is because it's going to become a little bit familiar later on when we look at the matrix notation. So this is a weighted least squares adjustment. A weight is being applied to each residual. So practically speaking, the longer the distance, typically the lower the weight. This means the residual can actually be a little bit higher on these longer distances. Now I won't go too much into weights just yet. We'll come back to them. So let's recap. An unweighted least squares adjustment, which when dealing with a single dimension is known as linear regression, is completed by minimizing the square of the residuals. A weighted least squares adjustment, also known as weighted linear regression with one dimension, is completed by minimizing the square of the residuals, including the weights, which is minimizing the sum of R times W times R for each observation. So jumping back to the least squares adjustment summary, we're now going to look at this A-posteriori variance factor and the chi-square test. So what is the A-posteriori variance factor? What does it tell us? Well, according to matrix notation, the A-posteriori variance factor is the following. S squared, which is the variance factor itself, is RT, residual matrix transposed, multiplied by the weight matrix, multiplied by the residual matrix. But what does that mean? And for those of you who are still awake, something look a little bit familiar here. So at the risk of repeating myself, let's quickly go over the residual again. Firstly, your raw EDM distance observations are averaged, then they're reduced to the reference plane, corrected for any atmospheric scale effects. These reduced distances are used in the least squared adjustment to solve for the unknowns of the instrument corrections, index and scale. Then we add these instrument corrections to the reduced distances, compare against the certified EDM baseline distances, and the differences are the residuals. As residual is basically whatever is left over after everything else is corrected for. Now the weightings. The weight matrix is the diagonal matrix made up of weightings used in the least squares adjustment. A weight is simply 1 divided by the a priori uncertainty squared. So the a priori uncertainty or pre-adjustment uncertainty is made up by using all the different uncertainties, defining the uncertainty budget, as well as the standard deviation, or I guess you could think of it as the spread of the actual EDM distance observations you collect. So there's the weight there. 1 divided by a priori uncertainty squared. So a residual is a disagreement between the measured and the expected, and a weight is a representation of the uncertainty of what was measured. Just briefly touch on degrees of freedom. Degrees of freedom is the number of observations minus the number of unknowns. So for a typical EDM instrument calibration, we have 21 independent observations and 2 unknowns, index and scale. Number of obs minus number of unknowns, 21 minus 2 is equal to 19. So looking at this equation again, let's get rid of the matrices and just represent this without them. So mathematically speaking, we can think of this as the following. So the variance factor is equal to, for the first observation, residual times weight times residual. Then for the second observation, it's the residual times the weight times the residual. Same for the third observation, on and on and on. And for the final 21st observation, here's just another highlighted form of that. So here we go. This is the residuals times the weights times the residuals for all the different observations. So there's observation 1, observation 2, 3, 4, 5, 6, 7, etc., all the way to 21. So for each observation, we have residual times weight times residual. We have already defined what a weight is. A weight is 1 divided by the a priori uncertainty squared. So we can substitute that into the equation. Residual times 1 over a priori uncertainty squared times residual. And then we can simplify this. That equals residual squared divided by a priori uncertainty squared. And then we can actually make that residual divided by a priori uncertainty in brackets, all squared. So for each observation, what we essentially do is calculate the following, then we add them all together, We divide them by the degrees of freedom. Mathematically, you could think of this as the following. A-posteriori variance factor is equal to the sum of residual divided by the a-priori uncertainty all squared divided by the degrees of freedom. So we might be able to see that the a-posteriori variance factor is going to tell us something about how our residuals compare to our a-priori or pre-adjustment uncertainties. So what I want to do now is go on a little bit of a tangent, follow some theoretical examples, which will hopefully give you a bit of a better feel of what this looks like. So let's pretend we perfectly estimate our residuals, and they end up being exactly equal to our a priori uncertainties for all our observations. This is not very likely, but let's just follow the premise and see where it leads. So residual, in this case, is equal to a priori uncertainty, and I've just called them x. So residual divided by a priori uncertainty can actually end up being x divided by x, which ends up being 1, which you then square, which equals 1. So then when you sum all these together, the a posterior variance factor is going to be equal to 1 plus 1 plus 1 plus 1, on and on, 21 times. So there are 21 observations, 21 times 1 is equal to 21. Then we divide it by degrees of freedom, and we get a variance factor of 1.1. So the resulting a posteriori variance factor is pretty close to 1. In fact, the more redundant observations we get, the closer to 1 it will be. So this situation that I've described is really the goal we're aiming for. We want to get our variance factor as close to 1. So we want to go out and observe our EDM distance observations. We want to remove or account for any systematic errors and blunders, and then we want to accurately describe our weightings for the adjustment using the instrument parameters and the uncertainty budget. Then we run the adjustment. If we've done it correctly, then we get an a posterior variance factor of very close to 1. That indicates that we've accurately estimated the uncertainties of our measurements. So even if the uncertainty of our measurements was really high, as long as it's due to random error, it's not a blunder or a systematic error, and if we account for it correctly in the uncertainty budget, then we can expect to get a posteriori variance factor of close to 1. Doesn't necessarily mean our measurements are highly accurate. It means they have been accurately estimated. Their uncertainty has been accurately estimated. Okay, so let's go through another situation. In this situation, our residuals are twice as big as our a priori uncertainties, and let's see where that leads. So residual, I've called it 2x here, a priori uncertainty is equal to x. When we sub that into these equations, we get 2x divided by x. You can cancel out the x's, you end up with 2 squared, which is equal to 4. So then when we bring it into this equation, when we sum up all the observations, we get 4 plus 4 plus 4, on and on and on. 21 instances of 4. 21 by 4 divided by 19 is equal to 4.4. So in this situation, we end up with an a posteriori variance factor that is quite a lot larger than 1. Based on the degrees of freedom, I can tell you that this will fail the chi-squared test on the high side. We have not accurately defined the uncertainty of our measurements. Perhaps our uncertainty budget needs to be looked at. Perhaps we deviated too far from the guidelines set and our measurements are much less accurate than we think. Perhaps the temperature, pressure, and humidity at the closest bomb site is a little bit different to our EDM baseline. Oops. Okay, so situation number 3. In this example, our a priori uncertainties are going to be twice as big as our residuals. So residuals are equal to x, a priori uncertainty is equal to 2x. It's going to look much the same here. X divided by 2x is 1 on 2. So 0.5. When you square that, you get 0.25. So then you have 0.25, 0.25, on and on and on. 21 observations of 0.25 divided by the degrees of freedom. 5.25 divided by 19 is equal to about 0.3. So in this situation, we end up with an a posteriori variance factor that is much lower than 1. This will fail the chi-squared test on the low side, meaning we have not accurately defined the uncertainty of our measurements. Our pre-adjustment or a priori uncertainties are way too loose and are not realistic. Perhaps our uncertainty budget has some excessively large allowances for, say, centering on a pillar baseline, or you've set the expected temperature variation across the baseline to something really hot, some really high number, such that your adjustment can't fail. Well, you can fail the chi-squared test on the low side too, so oops again. Okay, so just a quick note, in all 3 of these theoretical examples, I'm cheating a little bit and just making all 21 observations have the same results when you look at their residuals and a priori uncertainties. This is purely to make it easy to understand as we go through it. When looking at theoretical example number 1, every single observation has the following result. They all equal 1, meaning the a posteriori variance factor equation looks like the following, which is just all 1s at the top. Do not expect to see this in a real life situation. Rather, you would be much more likely to see something like this, where the numbers are jumping around and there's a lot of random error, but in the end, it equals 1.1. Okay, so what is a chi-squared test? I briefly mentioned it, but let's take a look at it. So in Medjil, the chi-squared test looks like the following. Lower tail is less than 1 is less than upper tail. There are multiple ways to display the chi-squared test. This is just the way that Medjil does it. So the lower tail is the A-posteriori variance factor we've been talking about a lot, multiplied by degrees of freedom divided by the upper critical value. Similarly, the upper tail is the same, multiplied by degrees of freedom divided by the lower critical value. Now, I'm not going to expand too much on the critical values, but let's just take note that the critical values are dependent on confidence interval and degrees of freedom. So the confidence interval will always be 95% in Medjil. And in a typical EDM instrument calibration, where we haven't removed any legs and we're not testing for cyclic errors, degrees of freedom will be equal to 19. So effectively, under these parameters, part of these equations are constant. So if the following conditions are met, the chi-squared test fails. So if the lower tail is greater than 1, if this occurs, the test fails on the high side. And if the upper tail is lower than 1, and if this occurs, the test fails on the low side. So I can kind of reverse engineer here an acceptable a posteriori variance factor range that will pass the chi-squared test, assuming we are working with 21 observations, solving for 2 unknowns, and we have degrees of freedom of 19. So let's just quickly do that. We can move the equation around. 1.730 is the upper limit, 0.469 is the lower limit. So therefore, the acceptable range for the a posteriori variance factor is between 0.47 and 1.73 based on the above parameters. So theoretical example number 1, we have an a posteriori variance factor of 1.1. The chi-squared test is 0.64 is less than 1 is less than 2.35. That's a pass. Optimal result. Our a priori uncertainties are very reflective of our residuals. Excellent. Theoretical example number 2, that was the 4.4. That'll look something like this. 2.54 is less than 1. No, it's not. That's a fail on the high side. A priori uncertainties are too small compared to the residuals. Theoretical example number 3, variance factor of 0.3. 0.17 is less than 1. Yes. Is less than 0.64. No, it's not. That's a fail on the low side. A priori uncertainties are too large compared to the residuals. And here's an example of just passing. I've sort of created this using our range. So in this, our variance factor is 1.7. When we calculate the tails, we get 0.98 is less than 1. It is just. And then that's less than 3.63. You can see that this 1 is sitting very close to this tail. That's a pass just. This is the upper limit of an acceptable a posteriori variance factor based on the parameters that we're following through. And then another example of just passing, a variance factor of 0.5. So the chi-squared test 0.29 is less than 1. Yes, it is less than 1.07. Just. That's another just pass. This is the lower limit of an acceptable a posteriori variance factor. So let's do one more theoretical example. In this example, similar to theoretical example number 1, we perfectly estimate our residuals. They are equal to our a priori uncertainties. However, one pillar is unstable, which negatively affects 6 of our observations. So for these 6 observations, let's say our residuals are 3 times larger than our a priori uncertainty. So we have a bit of a split here. For 15 of our 21 observations, residual x is equal to a priori uncertainty x is equal to 1. So that represents this part here, 15 lots of 1. And then for 6 of the 21, I've called it y, just to make it distinguishable. It's 3y and y. So when we do this residual divided by a priori uncertainty, we get 3y divided by y. The y's cross out. 3 squared is equal to 9, and that represents this part here, 6 by 9. So we get 15 plus 54, we add that together, 69 divided by 19 is equal to roughly 3.6. So this also fails the chi-squared test on the high side. So when looking at our results, we need to dig a little bit deeper than just our variance factor, as you can see here. Because it could be, if you remember back to example number 2, we got 4.4 because everything was wrong. In this example, we're getting 3.6. We've actually got most of our observations correct, but because there's some unforeseen systematic error of pillar movement, that's affected some of our observations and has blown out our variance factor. Hopefully you're still with me. So back to the initial example, I've crossed out and I've covered the answer. Now let's have a little think. Will this adjustment fail on the low side? Will it pass? Will it fail on the high side? So we've got a variance factor of 2.48, and this is all those parameters that I was talking about earlier, 95% confidence and 19 degrees of freedom. So the answer is it will fail on the high side. So let's do some more digging. We failed on the high side with our chi-squared test. Now what does that mean? What do we do now? So as we've discussed before, fail on the high side could mean we have not accurately defined our a priori uncertainties, or pre-adjustment uncertainties, as a whole to all our observations. But it could also mean that there is some sort of other error source, systematic or gross error, still within the data set that we did not catch and remove. So first things first, let's take a look at this graph. You may recognize this data from earlier. This is the Medjil graph version of it. One thing to take note of is this little disclaimer at the bottom. Potential outliers are indicated in red if detected. So an outlier is any observation whose standardized residual is greater than 3, which we set up when we were setting up our EDM instrument calibration. We also have 3 observations here that have quite high residuals. So what's the standardized residual and why does it matter? Let's take a look at this extract from the table of observations, corrections, uncertainties, and residuals. So for simplicity's sake, I've just taken the first 2 columns and the last 3 columns. The first 2 columns from and to pillar. The last columns are the residual, which we've talked about a fair bit now. It's what's left over. We have the standard deviation of residual. This is the post-adjustment or a-posteriori uncertainty displayed at 1 sigma or 65% confidence interval. Note that this is different to the pre-adjustment or a priori uncertainty that we defined indirectly through the uncertainty budget. And then we have standard residual or standardized residual, which is calculated by taking the residual and dividing it by the standard deviation of the residual. So it's a product of these other 2 columns. So a couple of examples here. Pillar 2 to 5, take the data from here. To get the standardized residual, we just do the residual, which is 0.43, divided by 0.47, and we get the standardized residual of 0.91, which we can see there. Good, that's a good result. Pillar 3 to 4, standardized residual is equal to residual column 1.1 divided by 0.34 to get 3.27, which I've replicated here, and that is an outlier. There is only a 0.3% chance that a standardized residual equal to or greater than 3 sigma is not an outlier. So we have 1 outlier. Does it tell us very much about our data? Can we determine any patterns from this 1 outlier that might help us find a systematic error? Or is this 1 outlier just a blunder, single gross error? So what I would do here is let's rearrange these by standardized residual, absolute that is, and take a look again. Here we have the same result, sorted by the absolute value of standard residual. And here is our 1 outlier at the top, 3 to 4. What else do you see? Are there any patterns here? I think pillar 4 looks a little suspicious here. So from 2 to 4 and 3 to 4, they both have a positive residual of around 1.1 millimeters. You see that here, 3 to 4, 1.1, 2 to 4, 1.2. This results in a standard residual of about 3 sigma. 4 to 7 and 4 to 8 have a negative residual of around negative 0.9 millimeters. So here we go, 4 to 8, 0.97, 4 to 7, negative 0.9. And these result in a standard residual of around negative 2.8 sigma. 4 to 6 has a negative residual of around 0.4 millimeters, which is a standard residual of negative 1.2. That's not really a concern. 4 to 5 have a residual of around 0. But take note of the directions here as well. We've got a positive residual from pillars 2 and 3, and a negative from 6, 7, and 8. So here's a visual representation of the pillars to help us decipher it a little bit better. So from pillars 2 to 3, when measuring to pillar 4, we seem to see that these distances increase by around 1 millimeter. Then below, from pillar 4, 5, 6, 7, 8 onwards, particularly 7 and 8, we seem to see the distances measured get shorter of minus 1 millimeter from 4 to 7 and minus 1 millimeter roughly 4 to 8. Not quite the same with 4 to 5 and 4 to 6. So we're not seeing complete consensus, but 4 out of 6 of these seem to imply roughly a millimeter. One of them implies about half a millimeter, and then one of them sort of doesn't imply any movement at all. So just a quick reminder, what is an EDMI calibration? So we aren't using our observations to solve for the baseline pillar location. If we were doing that, we wouldn't see this pillar movement, we wouldn't find it, because it's systematic, it agrees. But what we're actually doing is we're holding the certified baseline distances, which is the position of the pillars fixed, to solve for the best instrument correction to apply to our total station. So essentially the pillars are the control data here. So our total station observations are being flagged as outliers because they do not agree with the control. So what do? We could go back, we could remove all the observations to pillar 4. Let's have a little think about what this does. Our number of observations would drop from 21 to 15. Our degrees of freedom would then subsequently drop from 19 to 13. This means our upper and lower tails on the chi-squared test will tighten up due to the degrees of freedom being lower. And this actually means our acceptable A-posteriori variance factor range tightens up as well. So it's just good to be aware of that. We could also do nothing. We have failed the chi-squared test, and our A-posteriori variance factor is a little high. But our instrument corrections are still pretty reasonable, and we still pass the statistical test A. So you need to decide on a case-by-case basis. For me, in this case, I have one outlier, possible movement of 1 millimeter, and to be honest with you, it's a Gold Coast baseline, which is a little bit more susceptible to slight pillar movement, so it could be reasonable to do nothing. So for the sake of this video, let's remove all observations to pillar 4 and see what happens. Be careful making this decision too quickly. In this instance, we can see 4 observations indicate 1 millimeter movement in pillar 4. 1 observation seems to indicate half a mil movement in the same direction, and 1 observation seems to not indicate movement at all. But I believe this is enough of a pattern to isolate that it is most likely pillar 4 that is causing the problems. But keep an eye out for other indicators as well. For example, what if it was only the observations that were observed from pillar 4 to the other pillars? This could also show up as 4 of 6 observations showing as outliers, but the cause might be the observations themselves from pillar 4. What about a high level of random noise in your data? This can appear like you have specific outliers, either in pillars or individual observations. But as you start to remove outliers, more and more outliers continue to pop up. The true cause might actually be just generally high noise and random error in your observations as a whole. However, some of them just happen to agree more than others. So for more information on how to actually remove observations, please refer to the video guide that introduces the use of Medjil. There's a section at the end there about how to reprocess and remove observations. Okay, so what's the results of changing these? So instrument corrections. On top here, I've called it before, which is the 21 observations, including pillar 4. And then below, I've called it after, which is 15 observations with all 6 observations to pillar 4 removed. So what happens here? Well, over here I've written, this is what changes. Index value changes by 0.14 millimeters less. Scale value is 0.33 parts per million less. Index uncertainty is 0.11 millimeters less. Scale uncertainty 0.42 parts per million less. So basically everything tightens up in our instrument corrections. So that's a pretty good indicator that we now have a better result. Let's look at the least squares adjustment next. So on the left here, we've got the before 21 observations and after. This is removing pillar 4. We can see that our a-posteriori variance factor that goes from 2.48 to 0.98. Excellent. Now, what does this mean for our chi-squared test? It goes from being a fail to being a pass. This is a near optimal result that we talked about earlier, very close to 1. So this is a really good sign that once we remove the outlier of pillar 4, our uncertainty budget, which we've used to determine the a priori uncertainty for each observation, is actually a really good estimate of the resulting residuals of each observation. So I showed you that theoretical example 4 earlier. That really seems to be what's happening here. Moving on, let's look at the residuals and the standard residuals. So with the before adjustment on the left, we see we've got 4 observations with a standard residual larger than 2 sigma. So remember, 2 sigma represents 95% confidence. So there's a 5% chance of something being larger than 2 sigma. I guess being reasonable would be the way to say it. So this, in 21 observations, to have 4 seems a little bit statistically unlikely. But anyway, once we remove those observations to pillar 4, and we come over here to our after, our largest standardized residual is about 1.8. So that's really good. So let's bring up a graph again, see if we can visualize what we've just done by removing these pillars. So here's the original adjustment, which I had labeled as before, which is all the 21 observations, including pillar 4. So firstly, let's add in our upper and lower bounds of the instrument correction. The upper and lower bounds are using the instrument correction values along with the uncertainties at 95%. So the upper bound is the instrument correction value plus the uncertainty, and the lower bound is the value minus the uncertainty. The lower the uncertainty of the instrument corrections, the more these bounds will actually tighten up around the instrument correction line. It's just a way to represent the corrections as well as their uncertainty for comparison. So here are the 6 observations that we're going to remove that include pillar 4. We can see that 4 of them sit outside the upper and lower bounds. These are the 4 values we highlighted earlier that have a standardized residual that is larger than 2 sigma. So let's remove them and readjust. So I've just kind of blanked out the original adjustment, and in green we can see the new results. See, a lot of these observations at the shorter distances down here have actually moved down towards this 0 line. Some of these longer distance observations are moving up towards the 0 line too. We can see here a couple that are actually moving away. So let's clean this up a little bit. Okay, now let's add the new line of best fit for the instrument corrections. Looks pretty similar. Let's add the upper and lower bounds for the new instrument corrections. In purple, we can see the adjustment with the observations to pillar 4 removed, sitting on top of the original adjustment in orange. We can see the bounds have moved closer together towards the line of best fit, as the uncertainty of the instrument corrections are lower. So hopefully this will make it a little bit easier to visualize what happens when we remove these observations. So in summary, removing pillar 4 seems to improve the result. It seems quite likely that there has been around 1 millimeter of pillar movement in pillar 4. So it's time to panic and call the department. Well, maybe, but make sure there's no other issues with your data. If you have deviated from the EDMI comparison procedure, particularly in a way that would lower the accuracy of your data, it may not always be quite what you think. But please feel free to reach out. We will most likely access your raw data and reports through Medjil, and we may ask you to provide more information. A quick little word of caution when removing pillars. It can seem like a great little fix, but sometimes you end up chasing your tail trying to remove pillars. So you might remove one, then you're left with another pillar that looks like an outlier, so you remove it, and on it goes. That's often representative of a little bit more going on than just pillar movement. So jumping back to Medjil, we've discussed quite a lot about the least squares adjustment summary. I just want to take note that we're looking again at the original calibration that includes all the observations, including those to pillar 4. Just for the sake of simplicity and consistency, I'm just going to stay with that report for the remainder of the video. So in summary, we see our A-posteriori variance factor of 2.48, which we know fails the chi-squared test on the high side, which in this case we have attributed to a little bit of movement in pillar 4. So let's keep moving on. So we've looked at statistical test A, which we did pass. The statistical test B compares subsequent calibrations with the same EDM instrument to one another. So in my case here, I've only got one calibration in Medjil with this instrument, so the test is not performed. This test is not being performed due to insufficient historical records. But the test basically looks to compare the calibration results. It's actually specifically the experimental standard deviation, which I haven't really talked about much, between the calibrations to determine if they quote-unquote belong to the same population. I have not dug too deeply into this. These actually originate from the ISO standards. But if this test failed, it might indicate there's a significant statistical difference between the EDM instrument calibrations, and that might need investigating. Then we have statistical test C, which looks to test if the 0-point correction, also known as the index correction, is statistically insignificant. I think you'll mostly find that this will fail, representing that statistically speaking, you should correct for your 0-point correction if you're able to. As such, for this test, you basically just need to confirm that you're comfortable with the amount you see here for your 0-point correction. So then moving quite quickly, we have the calibration distance observations. This is basically all the raw information you put in, and then it averages them, looks at some of the standard deviations. Nothing too much to report here really, but this could be something you look at to try and identify a problem. Then we have the summary table of distance reductions, which is basically just an overview of what we just scrolled past. So the average slope distance talks about the corrections we've got here from your atmospherics, your offset and your slope, and then your reduced distance. So what you're seeing here is your slope distance getting reduced onto the reference plane, accounting for the atmospherics as well as offset and slope. Next, we have a summary table of Apriori standard deviation contributions. So this is representative of the Apriori standard deviations or uncertainties that are basically being populated, some of them through the uncertainty budget and some of them through other sources that are being attributed to each of your observations. So here we go from pillar 2 to 3. We've got the EDMI measurement uncertainty is 0.13, and we've got temperature, pressure, humidity, certified distance, centering, height, offset. So this is basically representing the uncertainty of the measurement from all the different sources, which gets combined together to become the weighting in the least squares adjustment. Then we have a little bit more information about the uncertainty budget and the uncertainty sources. So some of these are set in the uncertainty budget, and some of these are calculated on the fly. So certified distance here, it's got a formula here that is used to calculate these uncertainties. The EDMI calibration, once again, it's got a formula here. So this is dependent upon your data, but some of the other ones here are not dependent on your data. For example, expected variation along measured distance is set in your uncertainty budget. I won't go too much into depth here. Some of this is a little bit complicated, but basically this is a full report of all the uncertainty sources. Then that gets combined together in the combined uncertainty budget, total distance uncertainty. Then we have a little table here that talks about the uncertainty group contributions to certified distances. One of the biggest things about this table you need to keep an eye on is this scale down here. Sometimes if you have some sort of error in your thing, this scale, maybe this number will go up to, I don't know, say 5, for example. And these offsets, the heights, centering, all of these will be barely visible, and it might show you maybe that it's your temperature, or maybe that it's your EDMI calibration that's causing a lot of the error. And that can be used to sort of problem solve your adjustment. Next, we have the table of observations, corrections, uncertainties, and residuals. So I pulled data from this earlier in the video. This is a very helpful table. It has a lot of information. It basically has everything in it. So this table doesn't print very well, but what it is good for is that you can actually just select the whole table and put it into Excel if you want to dig a little deeper into what's happening with your data. So if we scroll over, particularly these last columns I use a lot. So we've got the residuals, the standard deviation of residuals, and the standard residuals. You can actually click on a header to sort it. One little problem with that is that the standardized residuals are sorted by not absolute. So you actually have the worst ones here and the worst ones down here if you're going back and forth. So that can be a little bit tricky. Next, we have the ISO full test procedure. For more information, look at the technical manual. For most users, this is probably going to be beyond the scope of what you want to look at. The full test results, the full test procedure least squares adjustment. Then we have the residual from the least squares fit of baseline measurements, which we've also looked at a little bit already. This can just help you identify outliers and identify observations that have big residuals. So one thing to note is when you hover over it, it tells you the baseline observation, so 3 or 4, but on the graph it's showing the residual. So residual in millimeters, it's just above 1, but when you hover over it, you get the standardized residual 3.27. So it's sort of showing you quite a lot of information altogether. Comparison of raw observations to certified distances is pretty similar to the table above. Next, we have the return phase angle of observed distances. Once again, this is probably beyond the scope of most users, but this is looking at the cyclic errors. Then we have the EDMI calibration history. The report notes, it's quite a bit in here as well. Any data warnings, and then finally you can type in who entered it, the position, put a signature, date, and save it. So hopefully that gives you a bit of information about how to look at an EDM Instrument Calibration Report. I haven't gone into everything in a lot of detail. I've skipped over a lot of things very quickly, but I've sort of labored on a few specific points. The things I focused on, the least squares adjustment, statistical test A, standardized residuals, those are really the things I look at first when it comes to trying to understand how my calibration went. The goal of these 2 videos was to hopefully preemptively answer the common questions you might have about Medjil and about analyzing the calibration report. But if there's something I have missed, you can contact the Geodesy and Positioning team at the Department of Natural Resources and Mines, Manufacturing and Regional and Rural Development at geodeticssupport@nrmmrrd.qld.gov.au. Hope it was helpful.